Chapter 27, we are at the end. This is the last chapter in the book. We're still doing hypothesis tests and confidence intervals, but this time we're applying it to linear regression. So it's what we learned way back in Unit 2. So let's say we have this scatter plot, and it displays all the 178 half marathon times for a professional runner. The explanatory variable, that's the x variable, is the temperature on race day, and then the response variable, that's the y, is the time it takes to run the race in minutes. Now, this is the population of all their half marathon times, and we're going to sample just 11 of these races. So we randomly select 11 values, and we get the results in this table right here. And before we do anything else, let's do a refresher on regression. So we want to make lists of both of these in our calculator, and we want to run the regression using the directions here, either for TI-84 or TI-89. Okay, it's going to give us an output. We want to write down these values, A, B, R squared, and R. The R is the correlation coefficient. It's telling us how well this data fits the line of best fit. The R squared is the coefficient of determination. We want to look at the scatter plot, and we want to look at the residuals plot by putting them into one of our plot setups. Okay, and from all that, we can get this equation. Time hat equals 139.5 plus 0.069 times the temperature. Now another refresher from Unit 2, if we were asked to describe this association, we would use the acronym FUDS. We would want to talk about the form, this is linear, any unusual features, there's nothing that really jumps out, but maybe we can talk about these 2 points up here. Direction is positive, and strength is moderately strong to strong. So we could say the association between the temperature on race day and the time it takes the runner to complete the half marathon is positive, linear, and strong with no unusual features. Okay, this value we get from the calculator. The correlation coefficient of R equals 0.811 indicates that, generally speaking, as the temperature rises, the time to finish the race increases with it. Now, there are a lot of things that we can be asked about this line of best fit equation. For example, interpret the slope. And the slope is the number that's attached to our explanatory variable temperature, 0.069. For each increase in 1 degree Fahrenheit, we expect the time to complete the marathon to increase by an average of 0.069 minutes. As this goes up by 1, this goes up by the slope. Interpret the y-intercept, that's our 139.5. If this runner completed a marathon in 0 degree weather, we would expect it to take 139.5 minutes. Coefficient determination, this is the R squared value. So if we square 0.811, we get 65.8. 65.8% of the variation in the time required to complete the marathon can be explained by the temperature on race day. And lastly, if it talks about residuals, residual is always observed minus expected. So residual for a 46 degree 142.1 minute race. This is the actual time it took them to complete the race when it was this temperature. We can find an expected time by plugging in 46 and we get 142.7. In actuality, they got 142.1. Always actual minus expected or observed minus expected. We get a residual of negative 0.6. They finished the race quicker compared to what we expected them to finish it at. Now that we're done with the refreshers, let's think back to that first slide where we saw the scatter plot showing all 178 half marathon times and the temperatures. This equation right here and all the equations that we did back in Unit 2 were based on a sample. Here we took 11 values from that 178 and we got this equation. Just like every sample, if we took a different 11 values, we're going to get a different sample result, which means our slope is going to change, our y-intercept is going to change, right? But there's actually a true slope that may not be 0.069 and the true y-intercept, and that's what we care about figuring out in this section. So when we're dealing with a sample equation, it's what we've always been dealing with since way back in Unit 2. Y hat equals b sub 0 plus b sub 1x. In the equation for the population, we're talking about the mean y, or mu y, equals beta sub 0 and beta sub 1 for the slope. Okay, so beta represents the population compared to lowercase b's for a sample. Just like all the other inference methods that we've done, regression inference has its own assumptions and conditions. Unfortunately, they're not the same as the other ones. A key word to remember what they are is line, since we're dealing with a scatter plot. So the L stands for linear. We want to look at the scatter plot and make sure it's linear. If it's not, we can't complete a regression at all. Now we want to load up the residuals. These next three are all about the residuals. Residuals must be independent of each other. We're just going to write that into a sentence. We want to look at a normal probability plot of the residuals. Are those nearly normal? So we want to see something that's reasonably straight with no outliers in a normal probability plot. And lastly, the E stands for equal spread. Okay, again, we look at the residual plot. We want to see that that complete scatter with no patterns or anything like that. The same thing we checked for back in Unit 2. So when we have a problem like this, these are the steps that we go through to see if we can actually perform inference on our sample. We want to make a scatter plot. We want to check to see, is it linear? Is it straight enough? If it's not, we can stop. We can try to re-express it by taking, say, the log or the square root of the x's or y's. That's what we covered back in Chapter 10. If it is straight, we're going to run the regression. That creates the actual residuals. We make a plot of those residuals to make sure they don't have any pattern. And if that's okay, the residuals look approximately normal, conditions are satisfied, we can go ahead and complete either a hypothesis test or a confidence interval. So let's start with a hypothesis test. Based on our sample of 11 values, is there an association between the temperature on race day and the time it takes for this runner to complete the half marathon? Use an alpha of 0.01. So the key phrase here is there an association? Okay, and then we have two quantitative variables, temperature and time. All right, here was our data, and we want to do phantoms for a hypothesis test. So P, let beta sub 0 represent the true slope between the temperature on race day and the time it takes for the runner to complete the race. We are always doing inference on the slope, never on the y-intercept. Our null hypothesis is that the slope for these two would be 0, meaning that it's perfectly flat. There's actually no association at all between them. The alternative is that it's not equal to 0. There's some kind of slope, whether it's uphill or downhill, where there's an association between the temperature and how long it takes to complete this race. Assumptions and conditions. The scatter plot of race times versus temperature is linear. I in line, independent. The residuals are independent of one another. For these next two, we want to actually show the residual plot. Okay, draw out the normal probability plot and say the normal probability plot of the residuals is reasonably straight with no outliers. Equal spread, sketch out the actual residual plot and say it's sufficiently scattered with no patterns. This is a linear regression t-test for the name of this hypothesis test. We put into our calculator, we get a test statistic of 4.1634, and degrees of freedom changes a bit from what we did in the last unit. It's actually n-2. So our sample size was 11. There's 9 degrees of freedom. Our p-value is 0.0024, and we use that to make our decision. Reject since the p-value is smaller than the alpha of 0.01. State a conclusion. There's sufficient evidence to suggest that there's an association between the temperature on race day and the amount of time it will take for the runner to complete the race. If we're asked to complete a confidence interval, again, this is about the slope, not about the y-intercept. We're going to use an alpha of 0.01, so a 99% confidence interval. Parameter and assumptions we already wrote when we did the hypothesis test. Name the method. This is a linear regression t-interval for the slope. Put into our calculator, we get this interval of 0.015 to 0.123, and when it comes to interpreting this, it's almost like we did when we did two sample differences in chapter 22 or chapter 25. So this is telling us what do we believe the slope is based on our sample. Okay, so we had a sample of 11 values, we got a point estimate for the slope, and from that point estimate, we make this interval. We expect that the true slope is between these two values. So we write it like this. We are 99% confident that for every degree increase in temperature, the mean amount of time it takes for the runner to complete the race will increase between 0.015 minutes and 0.123 minutes. So this statement is kind of like interpreting the slope from unit 2 paired with the difference in proportions or difference in means that we did when we're doing confidence intervals.